Here's a little background on me. I have a bachelor's and master's in electrical engineering from Georgia Tech. I have a PhD in artificial intelligence from Vanderbilt University, certificate in acoustical engineering, and I'm a registered professional engineer in the United States and a chartered engineer in Ireland. And you see the little RET there, I'm retired. You'll see that RET frequently here. So Ross has pressed me back into service here, for which I'm grateful. Thank you for the invitation. I used to be in the satellite communications industry, and you can see the pictures at the bottom of the screen that show some of the work that I got to do, I was privileged to do, including helping military communications and the Meerkat radio telescope project, which was down in South Africa. Very interesting. So that's enough about me. What I'm going to be presenting this evening is founded on work that was inspired me and inspired the common sense science scientists. Was Dr. Thomas Barnes. Dr. Barnes authored a number of books. People in the creation science world are familiar with him. He's had a number of articles that were published by the creation groups out in Texas and other groups. Here are some of his books listed. So he's kind of what brought all of us together. I chatted with Dr. Barnes back in probably the late 1990s, and he said, you know, I'm retired, so who you really need to talk to is this guy, David Bergman. And I didn't know David existed, and he gave me David's phone number, and I called David, and David was literally 2 miles away from me in Atlanta, Georgia at the time. That's when I met David. David left us in 2020, miss him a great deal, but a good bit of this work is his. And Dr. Bill Lucas, who currently lives in Maryland, is still with us and still doing some work little by little. And these are the two scientists who've contributed the most to this work that I'll be presenting to you today. All right, so why do this work? And you can find this on commonsensescience.net on the internet. The goal of these scientists has been to correct what we see as perceived deficiencies in modern physics. And to do this by going back to sound scientific methods that were used by scientists for centuries, actually, to develop better fundamental theories of the physical world. So common sense science is a body of theory that regards matter or physical particles and physical things that exist and the forces that interact between those things. And I'll get more into these details here about what it's based on later. Some of the foundational principles are based on the concept of cause and effect, and that the universe is fundamentally electrical in character. Applying these principles has led to two major things that I'll present. First is a universal force law, and I really can't emphasize how important this is going to be. And as we go along, I'll do my best to make it clear to you why am I spending time on this force law and how it came about. And Lord willing, I'll do a good job of helping you understand why that's the case. And the other thing are physical models for elementary particles. So we'll get to each of this in turn. So the title, Physics, What's Still the Matter? It's a play on words, of course, but from our point of view, we think that the world can be described using fully physical models versus using abstractions, such as a point particle, which is a mathematical abstraction. Of course, even modern physicists, some are using physical models now. There's change ongoing at all times, but the predominant view still has a great deal of abstraction rather than physical models is not the emphasis. We think that just as at the atomic or molecular level, where we have solids, liquids, gases, is very physical and we can see the mechanics of how things work, we believe that even the subatomic realm and the cosmic realm are just as structured and obey the same laws of mechanics, and I hope to show that to you. This presentation is going to describe forces, structures, and then the characteristics at the particle level that have been developed by the scientists, Dave Bergman and Dr. Bill Lucas. All right, so here's our outline. We'll talk about what matters first, just to carry on the little play on words theme. We'll do a series of slides on deriving this universal force law, and I promise it won't be heavy, boring mathematics. Well, maybe a little bit of mathematics. We'll look at the derivation of the gravitational force, which comes from the universal force law. We'll then look at an electromagnetic model of matter. We'll look at derived features from that model, such as mass, the neutron, and so forth. We'll look at a new atomic model, so we'll move from particles up to atoms. We don't have time tonight to look at a subatomic, as in particle physics, where you bang things together and break them into pieces. We don't have time for that, but those of you who get a copy of the slide deck, I have a series of slides on the subatomic particle model from Common Sense Science in the appendix at the back end. And then we'll draw a few conclusions. All right, ready? I can't hear you. This is the terrible thing about Zoom, is it's a lot better to be in a group and be able to hear the group. So my apologies that I can't hear you, but hopefully we'll have time for questions. Okay, so what matters? Size matters. Play on words again, but we're going to talk about the size of particles. The shape of these particles matters. We think normal time as opposed to time dilation or warped space-time, that normal time matters. Normal three-dimensional space matters as opposed to warped space or curved space. What the forces really are and where they come from matters. And understanding what an electron and a proton and a neutron, what those things actually are, matters. So we'll take these in turn. All right, so I first have to teach you a little something about distances. All right, so let's start with two charges here, two charged particles, Q1, Q2, red and the blue. Now, here's what I need to introduce you to. Those of you who aren't electrical engineers or radio engineers may not be familiar with the term near field and far field. In fact, many physicists are not familiar with these terms unless they expressly took electrical engineering radiation types of courses. By radiation, I mean electromagnetic and not nuclear. So I want you to understand what the near field is and what the far field is, because misunderstanding this, we think, is a source of a lot of mistakes that have been made in physics. Okay, so if I want to calculate the force between these two particles, we would use Coulomb's law written over here on the side. And it's pretty simple. It's the one charge times the other charge divided by the distance squared. Fair enough? It's not too heavy duty for mathematics. All right, but what is this distance? Normally, it's the distance from the center of one particle to the center of the other particles. So if these particles are small, let's assume that they are close to point particles. Then the distance from the center of one particle to the center of the other particle is actually almost the same as the distance from one edge of a particle, if it has a size, to the edge of the other particle. Okay, can you see this as we're going along? I hope you can. All right, so in this case, the minimum distance between any portion of one particle to any portion of the other particle, that minimum distance is pretty much the same as the distance from the center of one particle to the center of the other. So if you use Coulomb's law and calculate a force between these two particles, whether they're attracted or repelled, it doesn't matter, you'll get a force value, a magnitude that is reasonably correct. All right? Now, in antenna theory, when you have little small particles and they're really far apart compared to the size of that particle, that's called being in the far field. Each particle is in the far field of the other particle. That's going to be important, so try to hang on to that. So in a far field, any radiation from that particle tends to vary with 1 over r squared, which is like the normal radiation from a light bulb, okay? It varies with the distance squared. And we would call this a spherical source of radiation. That's the far field. All right, now, what if these little point particles are so close together that we assume they're a point, but maybe they're not. Maybe they've got a little size to them, kind of like my red dot and my blue dot here. All right, so they're not zero sized. And now the distance from the center of one particle to the center of the other one is actually a bigger distance than the minimum distance from any portion of one particle to any portion of the other one. All right, does that make sense? Sadly, I can't hear you say, yes, that makes sense. Hopefully that's what you're saying. All right, so in this case, the minimum distance is less than the distance from the center to the center. Now, if you use Coulomb's law, but you use that center distance, you'll get a force value. You'll calculate a force value that's too small. The force is actually stronger than what you calculate. And the reason is a portion of each particle is actually closer together than the distance that you used in the denominator of Coulomb's law. This mistake, assuming that the particles are points and don't have any size, caused people to conclude over 100 years ago that Coulomb's law was wrong at the subatomic level. Now that's why size matters. All right, so from antenna theory, this situation you're looking at is called the near field. It's when the particles are close enough to each other that their size or shape or orientation may matter in how they affect each other. All right, so what if particles made of charge are really some kind of shape, some kind of size? They're not a point particle. They're not infinitesimally small. What then? All right, is it really a little point, or might it be something shaped like a ring? Not even a big ball, but maybe even a ring. Let's see. Let's see if size and shape matters. All right, so now let's do this exercise again. I got a charge on the left, but it's really got some shape to it. In this case, I've drawn a ring and a particle on the right. The distance from center to center in this case is still pretty close to this minimum distance. Wouldn't you agree? They're approximately equal to each other. And in this circumstance, Coulomb's law will still give you a reasonably correct answer. This is called a far field circumstance. The other particle is so far away that it appears like a spherical source to me, or like a little point particle, because I'm far enough away from it. But now we move them closer together. Now you can see that these particles have some kind of size, and the distance from the center of one to the center of the other is much larger than the minimum distance between the two particles. So in this case, again, if you use Coulomb's law, but you use that center to center distance, again, you'll get a force value that's too small. And why will the force be too small? Because you use too big a distance. Portions of these particles are closer together than the number that you used. So to solve this, you actually have to do a little more complex math. You have to do what's called an integration across the shape of each particle and use Coulomb's law iteratively or repeatedly to get the correct force value. But if you did that, Coulomb's law is precise. There's nothing wrong with Coulomb's law. This is a near field circumstance where the size and the shape of the other particle now matters. So generally, you can see in the heading at the top of the slide, if it's less than 10 times, the distance they're separated is less than 10 times the size of the particle, you're considered to be in the near field, and you have to take into account the shape, size, and orientation of the particle. Let's look at this one more time. What if I took these two ring-shaped particles and I flipped them up like this? All right. Now they appear smaller, and the distance from center to center is very close, or approximately equal to the distance, the minimum distance. And again, in this case, you'll get a Coulomb law answer using the center distance that's close to the correct answer. So the orientation of the particles may matter in the circumstance. All right. A precise force would still require integration across the shape, doing some good calculus there, which we'll let Ross do in his spare time. Okay, so don't worry about that. All right, so is this a far field circumstance? If the size of the object in terms of how it appears is small compared to the distance, it's the far field. All right. Now, here's some basic postulates that we have. Size matters. I've already showed you that with Coulomb's law, and mistakes have been made. The shape is going to matter. If it's what we call a helicon ring, and helicon, by the way, is a term that's over 100 years old from Parsons gave us that idea. Time is going to matter. In our system, the time for a particle that's in motion, you see the little prime, or it looks like an apostrophe there. If it's a primed variable, that indicates the variable that's in motion. And if it's not primed, that's considered like the reference frame, or where you started the motion from. But the time in both frames is the same. The time is same everywhere in the universe, in our system. And space matters. We are going to use what's called the Galilean or Galilean transformation or Galilean space, which is what you and I think of as normal space. All right. I should back up one here. So there is the way you would translate. I'm going to come back to this little equation here, but if you've got velocity, you've got R represents the direction or orientation and the starting position, V for velocity, T for time. And then I've also included an acceleration term there. All right, if you had a changing acceleration, you would add another term. Do you see how this works? Depends on what kind of motion you're dealing with. But you would use the Galilean transformation, which is three-dimensional space, what you and I would call normal space. Now, what the forces are is going to matter. We're going to get to that next. And what an electron really is matters. Okay, so here we go. We've already moved on to the next item. Derivation of the universal force law. Number one, to do this derivation, and I'll explain why we got to do a derivation here. It's based upon assuming that the particles, the charged particles that have a force between them, and that's the force we're going to calculate, like the force of repulsion between two electrons or the force of attraction between an electron and a proton. That force is assuming that these particles are deformable, elastic, reshapeable. All right, that's an important concept because that is not a concept that's in current quantum physics, for example, in general. So we're not going to use point particles. We're not going to use mathematical abstractions. Now, all mathematics is an abstraction, to be fair, but we're not using complete conceptual abstractions. We're trying to use as physical a model as possible. All right, we're going to start with classical electrodynamics laws, and Galilean invariance is a fancy way of saying normal three-dimensional space, not warped, not curved, okay? We're going to assume local contact forces. Our theories do not use action at a distance. For example, something that's in the news a lot lately, quantum entanglement, which is a characteristic that's being exploited in quantum computers, is fundamentally an action at a distance. Einstein called it spooky action at a distance. But the point is, entanglement, there is no mechanism described as to why they're entangled. They struggle with controlling it. And this will satisfy also what's called Mach's principle. And Mach's principle is basically saying that the whole universe affects where you're sitting right now, and you need to take into account the entire environment that these charges that we're going to play with are involved in. If you ignore the effect of your environment, such as the gravity of the Earth, the gravity of the planets nearby, or of the sun, etc., you may be ignoring something that's affecting your results. That's Mach's principle. Okay, we're also going to use this Galilean transformation. right? Which means we're not using the Lorentz transformation that's used in relativity theory, which gives us bent space or time dilation and things like that. We're using normal time, normal space. And we're going to also pay attention to see to it that we conserve, we obey conservation of energy. And we'll get to why that matters here in just a few minutes. All right. Now, when we do this, you're going to find out that the force law that we end up with, or the force equations, account for acceleration, which special relativity does not do. It accounts for angular acceleration, also called rotation. And it accounts for radiation reaction, which is basically the derivative of acceleration or a changing acceleration. And these things have eluded both quantum electrodynamics and general and special relativistic approaches. What we're going to be doing here using these principles will also explain where relativistic effects physically where they come from. In other words, we don't need any reference to special relativity theory or using retarded fields. And you'll find out as we're going along here that relativistic effects mechanically come from the charge being deformable. The shape, size of the charge actually will change as you accelerate it. And that change gives you these so-called relativistic effects. But we'll get to that. And then the last slide with lots of words on it here is this is going to show that there is a new relativistic acceleration term. It's been missing from Maxwell's equations and other mathematics that are currently in use. It's going to explain many experiments, and here's a list of them. We won't spend time on them right now, but there are many experiments that have come up with results in terms of like motion of a gyroscope or other things that were not expected. The current laws of electrodynamics, which are fundamentally based on Maxwell's equations, don't work. They don't explain motion in a different direction or spiraling motion or that kind of thing. And what we're about to derive will explain that. Here's an example of what not to do and why all this stuff I've just told you in the background matters. All right, Maxwell took Faraday's law of inductance. Now, when you hear the word inductance, for those of you that are already glazed over here, inductance means there's a magnet involved, magnetic energy. And an inductor is a device that holds or stores magnetic energy. So fundamentally, if you don't take into account inductance in a situation, then you didn't obey conservation of energy. You just ignored the magnetic energy that was in the situation, for example. And this was one of the errors made by Maxwell. And in fairness, he didn't have enough experimental information perhaps to know that this mattered at the time. But these inductance or magnetic field effects were lost in this equation you see up here in the yellow box. And also the point particle assumption, which means he thought that all of the mathematics we're going to do is going to be in the far field. And that's fine if you're talking, you know, at the meeting room or tabletop level. But if we're talking down at the particle, atomic, inside an atom, inside a nucleus level, now you're in the near field. And this point particle far field assumption doesn't work. You'll get wrong answers. So what happens is Maxwell's equation in the form you see it up there, which relates, by the way, the E is in electric field, changes in the electric field, and how they relate to changes in B, which is a magnetic field. So that's all you're looking at up there in terms of the math. This form of Maxwell's equation, because of these two assumptions or errors in logic, gave the wrong answer, and it actually is what motivated Einstein to develop an alternative solution because they felt like the math they had was wrong. And so this was one of the key motivations for special relativity theory, but there was really some mistakes were made and they didn't pick up on those mistakes or acknowledge them. Now, just so you know that particles have a physical size, here's the first little piece of evidence. We'll come back to Robert Hofstadter's work here, but what you're looking at is he did electron scattering in 1956. That's how old this information is, okay? And in a neutron, you'll see the little dashed line down there. The charge of the neutron was positive up close to the neutron, but as you got further away, it swung negative. And the proton stayed positive the whole time, but it had that little hump there, which he couldn't understand. Point being, these are not point particles. As you get a distance away from them, and of course, look at the dimensions down there at the bottom, 10 to the minus 13th centimeters, okay, small numbers. But he could tell that these particles had a shape to them in 1956. He won the Nobel Prize for this work, along with another man. They shared the prize. Okay, so let's start over. Let's go back and kind of redo what Maxwell did when he combined Faraday's law and Ampere's law and Gauss's laws and so forth. All right, we're just going to go back and do it again, but we're going to do it with a few little changes. Try not to make the same mistakes. We're going to use all known physical laws, including two that Maxwell did not use. One is called Lenz's law. We'll come back to that. And Mach's principle I've already introduced, which means take into account the entire environment. All right, we're going to assume a finite size of the particle. We have to take that into account. If we're in the far field, okay, we can simplify things. But if once we're up close to a particle in the near field, now its size and shape is going to matter. We're going to assume that the particles might change in size and shape, especially if we accelerate them. We're going to assume that changes in the particles' electric and magnetic fields might occur. And I've already said we're going to use Gaussian or normal space and what's called invariant time. Time is the same everywhere at all times. All right, now here are the laws. There will be a test later, okay? You have to memorize all this. No, I'm just showing you the fancy stuff here. First, to see that there's 5 guys. Gauss gets credit for 2 of the laws, okay? So that's why there are 6 laws. And they relate electric fields, magnetic fields, motion, time. Those are what the letters of the alphabet that you're looking at there represent. So let's see why this matters, okay? First, 2 slides on Lenz's law, the law that was ignored for the last 100 years. Lenz's law basically says that if you induce an electric field, say by just like running a little generator, that's what you see there in motion. That's a moving magnet, a coil of wire. It generates electric power. We do this at every power plant in the world all the time, all right? Move magnets, generate power. We create electric fields. So the little E sub I, you see that little baby I down there? That means an induced field, a field we caused to appear from the magnetic energy that we put into the situation. Now, Lenz's law says that the induced field is proportional to the original, that's the 0, the E sub 0, the original electric field that was there. But do you see that minus sign in front of E sub 0? That means it's in the opposite direction. Does that sound like for every action there's an equal and opposite reaction? That's what it is. It's Newton's third law in electrical form. So an induced electric field will be proportional to and opposed to whatever field originated or caused it. If you've ever turned the crank on a generator, if you did that in high school, you got to turn the crank on the generator and light up the light bulb. As soon as you turn the light bulb on, you realize that the crank all of a sudden got really hard to turn. If you ever got to do that. Those of you in the room that got to do that, raise your hands so everybody can see, who the smart people are. Okay. Maybe if you didn't get to do that, you've been robbed, I'm telling you. But that's what happens. When you start generating electric power, more force is required to turn the crank. And more coal or more nuclear energy or more air or something, okay? So this is the math that we're going to use for Lenz's law. You can study that, and I'll hold it up and you can look at my little picture right here. But this is Bill Lucas's book, volume 1, on the universal force. That's what we're getting ready to derive, by the way. Bill Lucas, name at the bottom. You can see all the details for those of you who like this kind of math. For all the rest of us, let's move on. Okay, Lenz's law is basically an electric and magnetic corollary to Newton's third law of motion. For every action, there's an equal and opposite reaction. In other words, a change in a magnetic field occurs, and electric field is generated to oppose that change. Lenz's law is what's going to be key to us getting this math correct, because it reveals the physical origin that if a, and I'll show you later, but if a charge, this is what Dr. Thomas Barnes contributed. If you move a charge, moving that charge creates a magnetic field that creates a force that pushes back on the charge. And that force can reshape the charge. It's a feedback effect that's been ignored in physics for about 100 years. All right, here's a few additional things to support why we're doing this way. Induced fields, there's that little I, E sub I, and static or original fields are fundamentally different. You can't use what's called superposition, simply adding them together. Can't do that. They may be differently oriented and they're different in nature. But that was a mistake that Heaviside, Maxwell, and other electrical foundations people 100 years ago made, was they thought these fields were the same. Plenty of research work since then, though, has shown us. Fields of charges remain attached to the charge and they move with the charge. This is an important concept, so we'll come back to it. There are nonlinear effects we found in lasers and other devices, so we know we've got to accommodate that. Energy is conserved, momentum is conserved, which is another form of energy, it's just kinetic. Newton's third laws are valid in electrodynamics, in magnetics, action, reaction, and Mach's principle is valid. Okay, here we go. Here's the math, all right? All right, so now sit up straight. Here we go. Those equations that you just saw by Maxwell, excuse me, by Faraday, Ampere, the fundamental equations end up having 8 unknowns. All right, and we're going to solve for the first one there, F, which is the force. All right, we're just going to take the 6 empirical laws that I showed you, Ampere's law, Gauss's magnetostatic law, Faraday's law, all right, etc. Here they are again, just for fun, in red. Like I said, there will be a test. And the 2 equations from Galilean relativity, that the time when you're in motion, the primed t, is the same as the time for the portions of the experiment that are not in motion. And to describe motion, we're using 3-dimensional space, and we just need to pick the number of terms, velocity, acceleration, changing, etc., that we need, and plug it all in together and solve them as simultaneous equations. Now, why is that? Why are these simultaneous equations? Because they're all simultaneously true. They hold at all times. All right, so, and you notice that Galilean relativity is the one equation that could change. You may have to add terms if you have more complex motion that you're trying to analyze. All right, so you ready? You crunch on a bunch of math and you get 2 answers. Here's the first answer, which is the magnitude only, called the scalar potential. But I want to point out a couple of things. I've only used the Galilean transformation for velocity. You see it on the top right? I've got r, which is my radial vector that says what direction are we going, and that's a unit vector. And I've got velocity with time, all right? No acceleration terms, just velocity. Do you see that little v squared over c squared thing? All right, and in the denominator, what does that 1/2 mean? For those of you who know your math, it means square root. Square root of 1 minus v squared over c squared. There's your relativistic looking mathematics already have popped out of just simultaneously solving fundamental equations we've had for 100 years. And if I solve for the force, here it comes. You ready? All this stuff. Now, before you get up and leave, stand by. Notice that there are two terms. You see the plus sign there in the middle? Here, I'll help you out. Here's the radial force term, meaning you've got velocity, the speed of light, any angles that are involved in terms of the direction of the motion, that's the sine theta. But you see there's r there. That's the vector, and the velocity is the vector telling you the direction. And the radial force means, for example, between the sun and the earth, if we talk about gravity, but let's assume one's a positive charge, the other's a negative charge, they're going to be attracted. R is that little string in between the two. That's the direction of the R vector. That's the radial force term. But you see the second term here on the other side of the plus sign. That little term is what we would call a corkscrew force. And where do I get that? You see the little X's, the R cross V over C over there on the top right. Each of those little crosses says turn 90 degrees. So compared to the direction of R, you're going to have a force that is a left turn and an up turn. It's got two turns to it. So if I'm going straight ahead, but I've also got a force that is to the left and up, that's going to rotate me clockwise. It's like sticking your arm out and lifting your arm up. You just rotated clockwise. All right. Now, this is only for velocity, and this is the force law that we should have been using for the last 100 years, in our opinion. But it's got two terms. No one has had this second term until Dr. Bill Lucas derived it. And that's going to matter, and I'll show you as we go forward. All right, now let's do this one more time, but we're going to assume that we've also got acceleration involved, okay? Oh, one more thing, sorry about that. Notice that on both sides of the plus sign, for the radial force term, which is the primary term, and the corkscrew force term, they both depend on the same variables, which means they will scale up and down in a quantized manner. Now, this word quantized is going to come up again and again, okay? All right, so here we go. We're going to now add the acceleration term. Do you see it there in the r prime equals r minus the velocity times time minus 1/2 the acceleration times time squared. I've added that acceleration term. We're going to derive the force again. We'll solve all the equations simultaneously. And this detail is in Bill's book. Again, for those of you who want to go check his homework, you go for it. All right, here's the equation. That's a lot of math, isn't it? But let's simplify it. There's that little radial force term again over there. You see it on the left-hand side? Charge 1 times charge 2 divided by the distance squared. All right. And then you've got in the numerator both velocity and acceleration, which would make sense, right? And then you've also got the corkscrew force. And it's got a velocity component, r cross. Remember, the cross means take a 90-degree turn. So you two 90-degree turns, left and then up, let's say. R cross V. And you also have the crosses there in the acceleration term. You see how many there are? 3 of them. Each cross gives you a new direction for a force between charged particles. So these different directions explain why a lot of experiments seem to go wonky. Because if all you have is this over here on the left-hand side of the screen is the radial force term, if that's the only kind of math you've been using to describe your experiments, your answers are wrong. Because the natural force that the mathematics tells us is between charged particles has a second term that's oriented differently. All right, so here's the impact of these force equations, then we'll move on. First of all, we're saying that this force law, or these equations that we've derived which define a force law, define the only force there is, period, in the entire universe, at all scale sizes. There is no other force. There's just the electromagnetic force, and these equations describe them. Number two, notice that this second term, the corkscrew term, has previously been unknown, missing from physics mathematics, and it is in a different direction. Number three, so-called relativistic effects, for which we thought we needed time dilation and warp space and so forth. No, those effects are a direct result rather, of just doing the mathematics correctly and including Lenz's law, Galilean relativity, which is normal 3D space. And also notice that this is not just one equation. I derived this once using velocity terms, and then we derived it again by adding the acceleration term. If you're going to describe the forces between particles, then you've got to use all of the motion terms, which may include the derivative of acceleration, which some people call radiation reaction. Some people refer to it interestingly as jerk. That's a changing acceleration. If you've got a big muscle car, you know what jerk is. So, all right. So I hope this makes sense, that you've got to derive the force law to have all the terms that are needed for the circumstance you're doing. All right, now let's apply this to see if it would apply to gravity. Is gravity potentially just a special case of this electric attraction and repulsion, or magnetic attraction and repulsion between charged particles? So here's how we start. We'll start with neutral matter. On the left side, I've got a positive charge and a negative charge, blue and red. And on the right side, I've got another piece of neutral matter with one positive charge and one negative charge. Now, you're all a bunch of smart people because you wouldn't be here if you weren't. So looking at neutral matter on the left and neutral matter on the right, should there be any attraction or repulsion between these things in a normal situation? Short answer is no, because they're neutral, electrically neutral. They attract and they repel equally. So there's no net force. But what if this matter is vibrating, meaning they're not just sitting still in space? Keep in mind, nothing in the universe is at 0 degrees Kelvin. Now think about that a minute. Even the black areas of space are at least 2.7 degrees Kelvin. So what that means, and of course galaxies and stars are a lot hotter than 2.7, right? So what that means is every particle in the universe is in motion. At least it's vibrating in place. Nothing is sitting still. All right, so let's start out here, and we'll assume that the electrons, that's the negative charge, they're lighter weight. So we'll assume that the positive charges kind of hang out, sit still, and we'll just calculate using vibration of the electron compared to its proton. All right, so we've got an omega-1, which is a frequency of vibration. We've got omega-2, and we've got an amplitude, all right, of these vibrations. All right, and then we can calculate forces. So you can calculate the force between the protons. That's what I've shown here with the dashed line. You see that? So we can use our force law, and we can calculate how much force is one proton repelling the other proton. And of course, you can then do that with the other particles. And if you'll notice, if you add up all the forces here, there are 4 of them. All right, proton to proton, proton to the far electron. electron to proton, electron to electron, etc. Okay? So we just have to do this math 4 times. And then as we go along, we'll get a whole bunch of terms. We'll have to make some reasonable assumptions about how big can the vibration of the amplitude be. We're going to assume it's no bigger than, say, the hydrogen or helium atom. You know, it's not bigger than the atom because nothing leaves the atom, so it's no bigger than that. We can make assumptions about frequencies, and we can average things over time and position and orientation, and you add it all up, and here's what you get. The sum of all the static terms, the force is 0. That's what we would expect, right? There's no net attraction or repulsion between neutral matter. And the contributions of the velocity squared terms aren't 0, but they average to 0. But when you get to velocity over the speed of light to the 4th power, those terms have a net value. And that value is a negative value, which implies that there is an attraction force, a force pulling or in the direction of pulling the particles together. So here's the math if you do all the math. Once again, all right, hang in there. We're going to make it simple. Notice there's 2 terms. One's on the top row, has a negative sign in front of the 2, and the second term is on the next row. And here's a few pieces. N is the number of atoms in one piece of matter, so this has been scaled up to more than the 4 particles we started with. All right. Z is the number of charged particles, or you can think of it like the atomic number, you know, what element are we talking about? So this would be generalized to any type of matter. Omega is the frequency of vibration, which would be the average frequency. And here are the 2 terms. First term in the blue box minus the second term in the red box. So the force of gravity also has 2 terms. All right, now this looks like a big mess. So let's do a little simplifying here, okay? So let's group some terms. Let's group that stuff and we'll call that G. Those of you who know a little bit about gravity might recognize that letter. And look down here is 45/8 times G. Interesting numbers, still G. And these 2 things are identical. We'll call that mass number 1. We'll come back to why mass is described in electromagnetic particle terms a little later. And there's mass number 2. So if we simplify and claim that these groupings of terms are G, M1, and M2, this whole thing simplifies, and there's more detail in Dr. Lucas's book. And also, this is the only theory that derives the value of G. Here's what you get, all right? There's the G, there's the M1, the M2. Notice the 2 terms. Does anybody recognize where that term comes from? Hint, it's on the screen there on the top. That term was defined by Isaac Newton in the year 1687. That's how long we've had that term. But this term has not been known for the 325 years since then. Dr. Lucas published his book in 2013. Discovered this work roughly the year before, or a little earlier than that, actually. And do you see the 2 crosses there? Make a 90-degree turn, then make another 90-degree turn, cross, cross. So the force of gravity has the normal between the 2 bodies force, that linear motion term in blue brackets, but it also has a second term that should cause a corkscrew motion. All right, so 2 terms. The second term is much smaller in magnitude due to the beta terms. Beta is velocity compared to the speed of light, v/c. So unless things take on a very high velocity, the corkscrew term will have a very small effect compared to the primary term. That's why people didn't notice it for a long time. But if you look at the Earth going around the sun, this is the one slide I'll show you. I've got some slides in the appendix which give more evidence of this corkscrewing going on in planets and their moons and so forth. But the Earth is actually going around the sun roughly at the equatorial plane of the sun. But as it goes around, it is taking a corkscrew. That's what the gray circles represent. They're not to scale. But the Earth starts out, let's say, at the top there, at the summer equinox, which is tomorrow, excuse me, not equinox, yeah. No, tomorrow's the solstice. There you go. Summer solstice. It's tomorrow, right? So tomorrow, summer solstice. Let me think where we would be on this. Longest day of the year. It might be on the, I think we're on the, no, that's right. Probably at the top. I'd have to get back and study my cosmology a little better here. But at any rate, what we're really doing is we're rotating like this. One rotation cycle per orbit because the two terms are quantized. They're based on the same terms. They're locked together. So the Earth does one rotation per orbit. And that's where you have your equinoxes when we're on the equatorial plane, and then your summer and your winter solstices when they're top of the bottom. So you end up having what looks like a tilted orbit. But your orbit's actually centered on the equatorial plane of the sun, but you have a rotation that you have to do. So down here, each green fiber, which is spiraling as it goes around the colored toroid, which kind of shows you its path, it looks like a tilted circle. That's what's going on, and the gravitational force law tells us that's what should go on. Okay, so other things that we don't have time for, but I will just give you a summary here. This force of gravity with the two terms also explains redshift with distance. It's not due to motion, it's due to gravitational potential changing with distance. As matter gets further apart from the center of the universe, there's less gravity. All right, they feel the effects of the rest of the universe less. And there's a lot of explanation that goes with that, and I'll let you study that in Dr. Lucas's book or in some of the articles from Foundations of Science. It also explains, since everything's vibrating, it should be radiating, and it does. And Dr. Lucas has actually calculated what the frequency range of this vibration should be, and it matches the cosmic background radiation, which is shown in the graph there. That radiation is emitted and reabsorbed by all the matter in the universe, but some of it's going to escape. And so as that energy escapes, you've got second law of thermodynamics coming into effect. We're losing energy in the universe over time, and the gravitational constant is losing its grip. And so the force of gravity is declining over time due to the radiation away of the vibration energy of all matter in the universe. And this decline in the force of gravity, there's evidence for it. We don't have time for it, but the Earth has expanded. There's evidence for that. People love to argue about it, but there's still evidence that is consistent with it. The Earth's orbit about the sun, we're creeping away little by little. The moon is creeping away little by little. I think they measure it in millimeters per year. Okay, the universe is getting bigger. Everything is losing its grip. All right, so we finished with the force laws. Those force laws matter, but now we're going to talk about matter. You ready? All right, first a little history. In 1915, Parsons introduced Ampere's notion from 1823 that he thought the electron was a very thin ring called Parsons' magneton. You can find that on Wikipedia and you'll get all kind of detail. So in a sense, the work that Common Sense Science is doing is literally a revival of this original thinking. Compton, Allen, and many others built on this model in the early 1900s, but then along came Rutherford, Bohr, de Broglie, and Schrodinger's quantum model, which became widely accepted roughly in the World War I time period there into the Roaring 20s. All right, ring models were then abandoned. In the 1950s and 60s, Winston Bostick extended this concept to a deformable, meaning reshapable, not a rigid ring. Barnes introduced self-field feedback effects. And then Bergman and Wesley showed that the ring's model and characteristics are consistent with a physical explanation for Planck's constant and other features. So let's see. There's also other evidence from X-ray and gamma ray scattering that show a ring shape, X-ray absorption, scattering experiments like Hofstadter's, and plasma injector, other experiments that Bostick did show ring shapes. So where'd this ring come from? Here we go. Pay attention. This is as good as the graphics get, okay, in this presentation. Let's start with a sphere of negative charge, all right? Ask yourself, if this is a big ball of negative charge, which should repel itself, why doesn't every electron, and every proton for that matter, fly apart? What holds that thing together? Because it sure isn't its electrical charge. Maybe there's something holding it all together. All right, so let's give it a spin. You take a ball of negative charge, if it is a ball, give it a spin, and what's going to happen? Charge in motion will develop a magnetic field. Thank you, Michael Faraday. Okay? Now, is this the shape of a magnetic field? Is it spherical like that? No. Magnetic fields are generally not spherical in shape. We're not going to worry about magnetic monopoles, which have been discovered right now. But those are fun to study and they fit this model. All right. What are magnetic fields shaped like? A donut. Toroid is the $5 term for a donut. All right. Now, this magnetic field, though, we happen to know that magnetic fields affect charge. It pushes back on the charge, and the pushback will be normal or perpendicular to the lines of magnetic force. All right. So that magnetic field, due to the spin, is going to push back on the charge. And if the charge is not rigid somehow, if it's reshapeable, it will reshape itself. And it'll start to shape like a automobile tire. And as long as the magnetic field pushes on it, it's going to continue to reshape until there's a balance, an equilibrium between the electric repulsion that wants to blow the charge apart and the magnetic field that's trying to implode it or push it in together. And look what kind of shape you're going to get. All right, so that's the fundamental basis of the model, our model of all particles. We call them a helicon. That's a term that was used by Parsons and since then other people. We'll get into the details of it, but the main thing is to notice the red lines and the black lines. The red lines represent the electric field that would emanate from this collection of negative charge. All right, and those electric field lines are trying to push the particle apart, make it bigger or explode it out. But then the magnetic field, the black lines, push in on the charge. All right, and they're trying to compress it, trying to squeeze it together. And it's the shape of that magnetic field that's dictating the shape that the charge will ultimately take. So the forces from the electric field energy and the magnetic field energy need to balance for this particle to be stable. And work by Bergman and others have shown that at known values for the size of an electron, rotation speeds close to the speed of light and so forth, give a very close approximation of these forces being balanced. So we think we've got a pretty good little model here. But here's the other part of this model, and I'd like for you to pay attention to this slide if you would. An electron, remember I said what matters? What an electron is matters. And what each electron is a ring, roughly ring-shaped negative charge collection of charge fibers spinning, but also it has a pair of fields, an electric field. That's how we know it's an electron, a negative charged item, is its negative electric field. In fact, that's the only way we know. And it also has a magnetic field because we can measure that. These fields are also part of the particle. You don't have the particle without the fields, and you don't have the fields without whatever charge is that forms the particle. Now, how far, think for a moment, how far do these fields extend? How far does that electric field go? It keeps varying with 1 over r squared in the far field when you're far away from the particle, all right? There is no sensible answer that would say it ever stops. It just keeps getting fainter, weaker, more spread out. So we believe, as did many other physicists before us, that the fields of every single particle extend to infinity. So everything in the universe, at least electromagnetically, to some extent, touches everything else in the universe. Does that make sense? All right. Failure to recognize that the fields are a part of the particle. It's not a wave-particle duality where it's a particle 1 minute and a field the next minute. It's both all the time. But if you ignore the fact that these fields are moving with the particle, then you'll end up with making misinterpretations of observations, such as the double slit experiment. Okay, let's keep moving. So here's a close-up of the electron. These charge fibers helically spin because the force law requires them to helically move as they orbit, as they go around. So you've got basically 1 or more. We think there are a minimum of 3 charge fibers that make up the electron. Each would be 1/3 of the total charge, of course, spinning around in a helical shape. You can see kind of the idea down there at the bottom right, where one charge fiber is blue, one's green, and one is red. The circumference is equal to the Compton wavelength. You can have multiple excitation states. We'll get into that later. It has physical spin and a physical magnetic moment, not an abstraction. The charge fibers could potentially be complex. There could be 3 primary fibers, but they could be composed of secondary fibers, which could be composed of tertiary fibers. There's much more on that we don't have time for, but just keep that as a concept in your mind. The more fibers there are, there's binding energy from magnetic coupling, among other things, between the fibers. That's going to affect, as we will see, the mass of the particle. So we'll get to that later. All right, so last slide or two on the helicon here. Electromagnetic energy in our model, the common sense science model, itself is purely wave-like. It is not quantized. It can be quantized in how it's emitted or how it's absorbed, all right? But the energy itself, in its essence, is purely analog, wave-like in our model. There are multiple sources of quantization, and I'll get to those. But one of those might be standing and oscillating waves, which are actually already been detected in particles. Particle interactions are, of course, determined by their electric and magnetic forces. That's the only force there is. And when you get up close, remember that term near field versus the far field? Up close and personal is the near field. Well, now the magnetic force is going to start to have a stronger effect because a magnetic field is not spherical. up close. It's not 1 over r squared. It's 1 over r more than that, depending on where you are when you're up close to the particle. So as we will see, because of the magnetic field's effects and the fact the particles have a size and shape, the electrodynamic force, electric and magnetic, can explain the entire atomic model without any need for a strong force or a weak force. There is only one force, the electromagnetic or electrodynamic, it's called, force in our model. Now here's a source of quantization that Winston Bostick came up with, and that is these charge fibers are connected. They don't break. They actually have tensile strength, and we can calculate what that tensile strength is, and it's a big number. So they are tough bands of steel. Think of it kind of like that, except steel's not strong enough yet. All right, so if you've ever worked with a bandsaw and you've had to take the bandsaw blade and store it for a while, when you twist the bandsaw blade, it pops into thirds. It doesn't just gently come together, it quickly pops and collapses. And this is what happens to these charge fibers. If they start to absorb energy, they don't really stretch or lengthen. The diameter stays about the same, but they can pop to a higher number of rotations. So you notice the 3 pictures over there. K is the number of rotations the charge makes as it goes around one orbit. All right, so the top, K is just equal to one orbit. But in the middle there, it makes 3 loops when it comes back. If it could absorb more energy, it would be 7 loops. But the transition is going to be quick because these are like bands of steel. They're going to pop from 7 to 6 to 5 to 4 to 3, etc. And that is a source of the quantized release or absorption of energy. This is a physical description of where quantized energy can come from. All right, so these words here on the screen are going to explain sort of the ideas that I just gave you there. The higher K numbers means it's more energy, and the fiber's continuous, so it's only going to have an integer number of rotations. You can't have, 3.5 rotations. That would mean the fiber broke. No, it's always going to be a whole number, and that change from one whole number to another is a quantized step. And this is one source. It's 1 degree of freedom. For those of you who know about degrees of freedom in system theory, the engineers in the room, this is 1 degree of freedom for which energy is absorbed and radiated from particles. There are others. Here's another one. Standing waves. So this fiber, as it goes around and is rotating, it also could be vibrating up and down, wiggling, so to speak, as it goes round and round. And these would be called standing waves. And standing waves in a ring are going to be a multiple of the size of the ring. And where does that lead us? That leads us to harmonics and the fact that you have spectra from hydrogen or helium that are harmonically, numerically related. And this is the source of harmonics in radiation. All right, we'll keep moving. All right, now we're up to, how are we doing on time here? Not too bad. We've been, all right, I'm going to have to close it down soon. All right, so let's look at the derived features. This is an important one. Mass. If mass was an intrinsic property, it shouldn't change with velocity. So if you have a particle accelerator, we find out that as we accelerate the particle, we have to use more force once it starts to approach the speed of light. All right, more force is required. Now that's interpreted in the common standard model, in the quantum model, as it's gotten more massive. All right. And this is the equation that describes it, where gamma is that familiar, you see where it comes from now, 1 minus v squared over the square root of v squared over c squared. All right. But in our model, mass is not more stuff. There's no more stuff in that particle. Rather, it takes more force to move it. And we'll see why. And that force is the measure of mass. In fact, that's how we know things are massive. It takes a force to move them. If we think it takes no force to move something, we don't think it has any mass. So mass is a reaction force when you try to accelerate a charge. So here's another example. Here's another particle accelerator. All right. So think of this as we accelerate the particle, we're transferring kinetic energy to it. This kinetic energy, all right, is going to cause charge in motion, is going to cause a reaction magnetic field, all right, which is an induced magnetic field, separate from its natural magnetic field just due to its spin. That magnetic field is going to push back on the charge. And that pushback is going to shrink that charge. All right. And when you shrink the charge, you just increased its charge density. That makes the electric field more intense at the surface of the charge, which now means you need more electric force to move it, because that's the only way we can move a charge is either with an electric field or a magnetic field. We don't have any other push stick in particle accelerators. The only push stick is electric or magnetic, because that's the only way to produce a force. So as the size decreases, the mass, meaning the force to move it, increases. So mass is a derived electrodynamic property. Here's an example as to why that's the case. When you compress something, you make it smaller, like a spring. When you compress a spring, you're putting energy into it. Even though it's smaller, there's now more energy there, right? That's the higher potential energy. And if you have compressed gases in an engine here, from the left side to the right side, the smaller size has more pressure, more potential energy. So the whole idea here is that when you make something smaller, it's more massive. So as the charge moves, the magnetic field pushes in, the charge is going to shrink in size, a higher electric field density, until you have a stable size. So electric and magnetic fields require more force to move them when they're stronger. It's more massive. And that's directly from Newton's second law here. Mass is equal to the force to move something to accelerate it. All right, so let's look at inertial mass. Now we're going to do the same kind of thing. We're going to have neutral vibrating matter, positive, negative charge, and we'll just have a positive charge over here and calculate the forces on that positive charge. So same kind of thing, add up the forces, and here's what you get down here at the bottom, all this math. A is the amplitude of vibration, frequency of vibrations omega, acceleration, so we use the acceleration terms in motion. So all of that is what defines the mass. Force is mass times acceleration, directly a result of the universal force law that Lucas derived. Now, let me give you two examples of why this is the case. Something called mass defect. If you take all the protons, neutrons, and electrons in any isotope of any atom and you add them all up, so here's the mass in atomic mass units of a proton, and by the way, there are different values for the proton. If you look online, which one of these numbers is the current one in use, I don't know. But you can use either one, it won't matter. You'll get the same kind of result that I'm about to show you. All right, so here's a copper atom. And by the way, atoms don't look like that, but I'm using this to help you keep track of what we're doing. You got a nucleus with protons, neutrons, and you got electrons out there, all right? So we're going to do the math. 29 protons in copper, 34 neutrons, 29 electrons. There's the total weight of each one of those things. You add it all up, you get 63.5 and some change atomic mass units. but the atomic weight of copper is 62.9. There's a discrepancy here called the mass defect of 0.6 and some change. All right, now the normal explanation for this is, well, that's because some of the mass is converted into binding energy in the nucleus, right? And we could do this for other things, for helium, for iron, for copper. Well, I did copper, but you add these up, there's a defect, meaning all the protons and neutrons, which are the primary contributors, they don't add up to what the atomic weight of the combined atom is. So here's a chart that shows you the mistakes or the mass defect. The red ones are where there is less mass when you add it up than it ought to be. But notice that there are some green bars. There are some elements, uranium being one of them, which is more massive than just adding up the protons and neutrons and electrons. So you can't use this missing mass converted to energy explanation for uranium or hydrogen down there at the other end, right? This isn't working out for them. In our case, that's because mass isn't stuff. Mass is going to change as the particle size changes, and the particle sizes in a nucleus are going to depend on the specific combination of magnetic and electric forces inside each particular isotope with a specific number of protons, neutrons, and we'll see what those are. Here's another version of this chart. All right. And you can find these online as well. So here's the second example of the mass doesn't add up. Nuclear fission. Here's nuclear fission, a diagram that shows a neutron hitting a target nucleus. It breaks into two main pieces and throws away a few neutrons, all right? Now, we're going to use uranium-235 as our example. There are 383 daughter products, nuclei. That's the two little fission products there that could come out of the roll of the dice when you hit a uranium nucleus with a neutron. Here's a graph of these things, of the two things versus their atomic weight, all right? And they range in atomic number from 29 to 63, copper up to europium. There's over 1,000 different combinations of what you can get when you split uranium-235. And you'll get somewhere between 0 and 5 neutrons each time you do it. All right, so let's take a particular pair. We split uranium-235 and we get cesium-144 and rubidium-90. All right, well, the first thing you'll notice is there's something called nucleon conservation. When you do this, you end up with the same number of protons and neutrons and electrons you started with. But there's a loss of mass, also called in this case a mass defect. Oh, Ross is sitting back down. Does that mean I have to stop?
No,
Oh,
keep going.
All right, I'm gonna keep rolling here. Now, the mass defect is the difference between the reactants, which is the neutron that hit the nucleus, and the fission products or daughter products that come out, including neutrons. So here's the specifics for cesium and rubidium. All right, so let's do it again. Now, if you're like me and you don't even know where these things are, this is a chart that hangs on my wall here. I got this, Vanderbilt University threw this away back in the 1990s, and I got it out of the dumpster. So down there is uranium, number 92, the largest naturally occurring element on Earth. All right. And there's cesium and rubidium right there. There's the two daughter products. You could get a whole bunch, remember, 1,000 combinations of daughter products, different weights and so forth. But we're just going to look at this one example, and this applies to all examples. All right. So do the math. Uranium has 92 protons. It's got a mass of 235. There's the details on the right. And then you add up cesium and rubidium and the neutron that pops out. And by the way, we included the neutron that came in. And there's a loss of 0.18 and some change, almost 0.2 atomic mass units. And of course, you can do that math in detail. And of course, using E equals mc squared, you can say that that mass got converted to 175 million electron volts of energy. In fact, this is the very principle that we generate nuclear power on. That 175 MeV is heat predominantly that comes out that we use to boil water and turn generators. Okay? But in our model, this is not a loss of stuff because you notice there is no loss of stuff. Same number of protons, same number of neutrons come out of the reaction that went into it. Instead, you didn't have mass converted to energy. You have one form of energy converted to another form of energy. That energy comes from a change in the size of the nucleons and the binding energy to hold them inside cesium and rubidium compared to the energy it took to bind and hold them inside the larger atom of uranium. All right, let's look at the real proton. Other characteristics here. The proton's based on the same helicon model, but the proton is more massive, so think about its size. That means it's 1,836 times smaller than the electron. And being smaller with its electric field squeezed like a compressor into a smaller space is what makes it more massive, because you have a stronger field intensity at the surface of the particle. It takes more force to move it. So it has a larger mass from intense electric fields. It also, we think, has more charge fibers than the electron has. It has a lower magnetic moment because of the small radius. The magnetic moment is different from just the magnetic field intensity at the surface of the particle, which would be higher for the proton. But the magnetic moment also depends on kind of how much leverage the particle has, and that would depend on its size. Being smaller, it has less leverage, so to speak. So it has a smaller magnetic moment. The other thing to know is that a bound particle is going to have a different radius than free particles because of coupling magnetic fields, and we'll show some pictures of that later. So here are the things that are conserved. Charge is always conserved. Magnetic flux is always conserved, and these two things are where Planck's constant comes from. Those two things multiplied together. That's why it's constant, because you always have charge and flux conserved. So anytime those things are conserved, Planck's constant applies as a limitation, because these are the limiting factors behind Planck's constant. We've derived, or these are, some of these are measured, but our model is consistent with these values for magnetic moment, mass, shape for the electron and the proton, and these are things you can see in some of our articles in Bill Lucas's book. Now let's look at the neutron, one more idea. This is Dave Bergman's model. And the neutron is not an independent particle. A neutron is simply a particular geometric combination of a proton and an electron, with the proton being much smaller inside the electron. They both rotate in the same direction, and this is consistent with Hofstadter's scattering experiments in terms of diameter of the negative being in red, the blue being the positive part. So the neutron's not an elementary particle. There is no elementary particle called a neutron. It's just an electron and a proton paired, which is why after 11 to 15 minutes, a free neutron always decays, releasing beta energy, which is the magnetic coupling energy, into a free proton and a free electron. So we should have taken this hint a long time ago, that a neutron is not a unique particle. It is two particles. There are only these two particles and their antiparticles, which we don't have time to discuss today. Okay, Hofstadter's information is consistent with this. I won't spend much time on these details, but the rest mass the size of the particle, of the neutron, and so forth is calculatable. It's consistent with our model and using the universal force law. And the beta decay energy is basically the energy of the magnetic coupling, which is what's holding the two particles aligned for a period of time. They stay together in a nucleus better than they do as a free particle. All right, one last thing, ether. Remember the electric fields and the magnetic fields of the particle, and how far do they extend? To infinity. And so when a particle moves, vibrates, changes shape, it's going to disturb its fields, radiate energy, which is a disturbance in its own fields. So each electric and magnetic field extends throughout the universe. They remain attached to and are part of each particle. Only charged fibers emit radiation and absorb it. Radiation is a disturbance in these static fields due to motion or changes in size and shape and so forth. Radiation is then carried on each particle's own fields. So the particle generates the radiation and the fields carry the radiation. So as a result, all forces are contact forces, and we don't need a third-party independent ether or medium to carry energy. This is the ether. It's the electric and magnetic fields of each particle create what people interpret as the ether. Here's just a graphic that kind of shows if you kinetically move the red particle, you can see how the lines of force are going to get disturbed, causing wave-type motion out away from it. And the graph at the bottom left shows another concept of that in a graphical form. All right, so let's summarize. Particles. All particles are a toroidal shape made up of charge fibers. There's at least three. There may be secondary and tertiary fibers. They all have intrinsic angular momentum. It's always conserved. The circumference is the Compton wavelength of that particle. You can have ground and excited states, physical spin, a physical magnetic moment. The electric and magnetic fields are attached to these fibers and they have tensile strength, which is why one particle can affect another. The tensile strength of the electric fields can push or pull on another particle. And radiated energy may be quantized and are carried on each particle's fields. So we're going to finish up here with the atomic model. Atom. We all know what an atom looks like, right? Well, maybe it's this electron cloud around a nucleus. And a nucleus looks like that, right? We've had these pictures imposed on us for years. Well, here's hydrogen. Hydrogen only exists as H2. You got two protons, two electrons. The protons are smaller, the electrons are bigger. That's not the scale. We'll get to kind of what the scale is. Because there's no such thing as a hydrogen atom. And oh my goodness, they are talked about everywhere. But in nature, hydrogen is a molecule. It's H2. There's no such thing as a free proton electron other than the neutron model I just showed you. Hydrogen ions exist, all right, which is just a standalone proton, but not a hydrogen atom, meaning one proton, one electron. It's talked about, the weight is calculated, etc., but it doesn't exist. Only H2. 4 particles is the simplest form of matter that is neutral and stable. Computer simulations can show that this type of geometry results in a stable minimum potential energy. What you're seeing in the second diagram is the oval is the magnetic line of force that couples the particles and aligns them. Magnetism is the much ignored force. The proton centers are 47% of the distance of the electron centers, which shows them closer together, but the radius of the proton is 658 times smaller than the electron, or vice versa. So they're not shown to scale here. If you did the scale on this, it would be really a lot of space. That's the hydrogen molecule. Simplest form of stable matter in the universe. That's it, 4 particles. And of course, the hydrogen spectra can come from adjustments in the radius, the K value in the terms of the number of rotations of one electron or both. All right, and we can calculate this spectra, and given time, I'm going to scoot ahead here a little bit on this. We've talked about that. This is a chart of the extreme ultraviolet spectrum, which quantum and other models could not predict. Bill Lucas's model of the of hydrogen, of the electron, calculated these numbers that are numbered here, the peaks that are numbered, and it corresponds to the NASA rocket probe's measurement in the shadow of the Earth of the extreme ultraviolet spectrum for hydrogen and helium. So our model is consistent with data that other models are not. Here's a model of a bigger atom. This is neon 20. Neon is element number 10. The nucleus is just shown as a little ball there. We're not showing the details of the nucleus. I'll get to that. But these are the electrons. In our model, electrons don't orbit. They have a fundamental position that's determined by electric attraction and magnetic coupling. The electrons, or the rings kind of in color, those are the lines of magnetic flux and great circles, which simply means that these are packed together as tightly as you can pack them together without the electrons' negative charge repelling them and pushing them further apart. Notice this is a great big springy system. You have electrical attraction and repulsion, pulling and pushing on things, and you have magnetic fields that want to always align with other magnetic fields, causing things to form alignments. And this is our model of the atom. It involves maximum magnetic coupling, minimum packing geometrically, with the forces of electric attraction and repulsion and magnetic push and pull in mutual balance. This is inherently stable and resilient. This is just the third shell shown geographically, geometrically here, of say copper or zinc. They both have 18 electrons in their third shell. This is sort of how the electrons would line up. Now, why do electrons appear to be a cloud? Because nothing is at 0 degrees Kelvin. These things aren't sitting still. They vibrate like freaking mad, moving all over the place, but they all have stability positions about which they're vibrating. So yeah, you got something that looks like this, and you give every one of these things a good vibration as you crank up the temperature to room temperature, which is 200 and something degrees Kelvin, right? Stuff's wiggling around a lot. But this is the fundamental physical model that we believe is there. There's your electrons, there's your lines of magnetic flux. Now, okay, number of electrons per shell. We can calculate what those ought to be based upon magnetic attraction, alignment, minimum packing. It's just geometry. And you'll come up with these numbers for each shell. All right. This model accurately predicts the shell progression also. So as you go up in atomic number, how many are in each shell and which shell they end up in makes sense because of just simple magnetic attraction, alignment, electrical repulsion of electrons with attraction to the positively charged nucleus. Simple concepts. This is the first causal explanation for these so-called magic numbers of electrons per shell. Here's a model of the nucleus. All right, so this is another part of the atomic model. This is oxygen. The little bitty rings are the protons. Remember, they're smaller. The big rings are electrons in the nucleus. Now, this is Bill Lucas's model, where the electrons and the protons alternate. If you use Dave Bergman's model of the neutron, where it's a proton inside of an electron, you'd have something that looks more like I've showed you on the right here. But and we don't know which one is correct. Both of these are theoretical models that both conform with the data that we know, but we just need more data. So let's stick with Bill Lucas's model here. There's your protons, there's your electrons. In the nucleus, there are electrons. Hello. We know this because every time a neutron comes out, in 11 to 15 minutes, it decays into a free electron and a free proton. And you also can have beta decay. Remember that? Which is an electron coming out of the nucleus. So we know they're in there. All right. Notice how they alternate, positive, negative, and notice there is nothing in the center. What could you put in the center? It's either going to be a positively charged proton or a negatively charged electron. That's all you got. There is no other matter to put there in normal matter. Because if it's positive, it's going to repel positive and attract negative. And so, in other words, there's no center in any nucleus. This is an important concept. Remember hydrogen? No center. It's very different from these images that are shown. All right. Now, let's look at the shells or the layering inside a nucleus. Here's how it goes. As you go up in atomic number and the total number of rings that you have in there, this is how it varies. Now, notice something. There's your possible shells and the number of particles in a shell. Notice that there's some missing numbers. You see that? In fact, as soon as you get up to atomic number 3, you don't have that inner shell of 2 anymore. You have a secondary shell of 3, 4, 5, 6, 7, 8 as you go up in atomic number. And then as soon as you get past 8 to 9, you develop a shell of 2 and then start building a shell, the 18 shell there that's further out. All right, these disappearing shells are a natural consequence of our model. All right. And the inner shells come apart because there's nothing in the center that helps hold or pull it all together. All right. And here's further evidence of this. This is a chart that shows the nucleus density, the density of the positive charge. And you notice as you get higher in atomic number, a bigger and bigger atom, it ends up having a lower positive charge density. That's because there's nothing in the middle. The inner shells come apart and you end up having just bigger shells of electrons and protons in alternation. The standard model, standard shell and the quantum shell model do not predict this. Our model does. All right. Another thing is nuclide spin. The quantum nuclear shell model gets all of these that are shown in this graph wrong. It does not calculate the total nuclide spin for a particular isotope correctly, but CSS's model of the atom predicts every one of them correctly. Now, why does the quantum model get it wrong? Because they have a planetary model where nucleons move about a center, but there's not a center. They don't have a mechanism for the shells to come apart as they get bigger. All right. And one more thing, the so-called liquid drop model, if you look at your shells where the dashed line is an electron shell and then the solid lines are a positive charge shell, you eventually reach a point where you skip an electron shell and you have 2 positive shells together. You see that gap right there? That causes the 2 positive charged shells to repel each other, and you end up with what's called the liquid drop characteristics, or the slipping in large atoms. And our model is consistent with this occurring because of the geometric nature of the model. All right. And lastly, here's the model of molecular bonds. We don't have time to go into this, but as soon as you go from atoms to molecules, the key thing is to realize that in addition to valence electrons attracting, which is an electrical model alone, you've got magnetic forces that are also causing the binding between various atoms. And this is why many chemists prefer this model, because it's got both electric and magnetic forces to cause binding, and that explains, for example, covalent bonds in a way that others have not been able to. So here's our conclusions, finally at an end. Our theories, we think, provide a uniformity that other theories don't. We have only one force, the electromagnetic force. There are only two building blocks of all matter, positive and negative charge fibers. It's consistent. It's consistent with all known laws, and there are no internal contradictions. It can be verified. This model is falsifiable. If we're wrong, it can be uncovered pretty quickly. And it's causal. There's no action at a distance. It's got all cause and effect touching force law derived. It's based on classical electrodynamics. Force is only due to electric and magnetic fields acting on charges. The universal force law includes acceleration and radiation reaction terms. That's a new accomplishment. It includes forces of a charge on itself as it moves, and successfully predicts many things. This next slide is more things that it predicts: nuclide spins, magic numbers, nuclear binding half-lives, relativistic effects. This model predicts all of these things. And atomic and inertial mass, because mass is not stuff, it is a derived property from the electromagnetic effects of particles. So I hope that you realize that Dr. Lucas's derivation of the universal force law has wide-reaching impact and application, should have, in my opinion. There's other work in physical models consistent with a broad range of data. I thank you for your attention and welcome your ongoing interest.
I have a question that's basically theological.
Okay.
Since God is a triune God, I always thought, that the three dimensions of space and the three dimensions of time, past, present, future, indicated that triune nature. And I was very distressed to hear that you call the force of the universe a singular force. How do you fit a triune God into a singular force?
Well, that's a good question. And the way or the approach that I would use to answer it is that Scripture tells us that God holds all things together. All right. And God's spirit is one spirit, even though he's a triune God. So we still have a trinity in this model, and that is we have positive charge, whatever that is. We have negative charge, whatever that is. And we have the electromagnetic force between these things. So it's a triune system in terms of the fundamental components that constitute reality, the way we see it. So I don't see, theologically, you might say, a necessity for the charge or the force to be triplicate or charges to be triplicate, but the system is triplicate, interestingly enough.
Thank you.
Thank you.
Thank you. Which, by the way, is over the centuries why secular scientists have often objected to some of the Christian scientists, Faraday, Newton, others who had some concept of God in their science, or at least motivating them in their science. Those who were secular objected to some of their ideas if they started to smack of God's spirit holding the world together, or things of that nature. And so we are where we are with a love for things that are random and chaotic and so forth for a reason that is beyond just the science.
How is Dr. Lucas? And you mentioned that the big G is decreasing.
Yes.
If the universe is expanding and we're losing matter from the cosmic horizon, would that affect big G also?
It does. The way, if in his book, for example, he spends a lot of time, on gravity and calculating it and sort of showing you how that is a logical sequence of events. But there's this concept of the center of the universe, which apparently can cosmologically be shown that there is one, and we kind of know how far we are from it, where we are on Earth in our little Milky Way galaxy and so forth. And as things get further away from the center of the universe, the gravitational constant changes, and hence that affects a lot of things. It can affect the speed of light. It can affect the strength of the force of gravity. It can affect the speed of radiation, or the wavelength rather of radiation, and hence it explains the redshift. So it's no surprise that the whole universe and everything is slowly decaying. We've kind of known that since the fall.
Okay. What books do you suggest reading to learn
Well,
this topic?
there's only one book I've got, which is Dr. Bill Lucas's book, The Universal Force. You can find it on Amazon last time I looked. But you can buy it directly from our website, commonsensescience.net also. And then we have, again, go online to commonsensescience.net, and we have a lot of what are called Foundation of Science articles. I haven't counted how many there are, but we're up to volume 24 now. And there's at least 3 or 4 per year or per volume. So those basically contain the physics that I've been presenting to you in small articles, one after another. And you can find just about all of them online. The last 2 years have not been posted online yet, but prior to that, they're all there.
Okay, and we're going to keep going, Dr. Collins. Maybe you can stop sharing the screen, then you'll be able to look at your questioners, I think.
Hello there, questioner. I can hear you.
Perhaps my question has been answered. The only publication available now is Lucas's volume 1.
Correct.
Will there be updates to it? And the Common Sense Science quarterly newsletter, I don't think has been published for quite some time. Is there going to be updates on that?
Okay, good questions. First, the book. He has revised the book, meaning mostly correcting mistakes that people point out, or errors, printing mistakes, and so forth. But the fundamental content has remained the same since he first published it in, I think, 2013 is my recollection. He has not yet produced volume 2, 3, or 4. Multiple reasons for that. Mostly Dr. Lucas has been in some accidents, physical injuries and stuff that have slowed him down, and caring for family members. So he has not been able to produce much more writing. And that explains your second question, which has to do with the Foundation of Science articles. Since Dave Bergman died in 2020, he was primarily the editor and the driving force to produce that. And Bill Lucas took that on, but with the other things that have happened to him, he has had less opportunity to produce more articles. So that is the sad answer to your questions, sir.
Do you have any other scientists coming on board who may step into some of these roles?
I'm going to answer that yes and no. We have had along the way a number of scientists, particularly as a result of conferences, physics conferences, Canary Islands and France and England and St. Petersburg, Russia, here in the USA, etc., that David or Bill attended and presented at. I've presented at a couple of them. And there are people who become interested in this model. And some, and particularly chemists, are very interested because of it. In their opinion, it explains covalent bonding and basically molecular bonding in a manner that other models haven't been as satisfying from their point of view. So, but how many people are making use of this? Can't say. There are other scientists, and I have some slides in the appendix. So if you do get the slide deck, there's an appendix on alternative scientific theories, because there are many, many of them. There's even a book of alternative scientists that's been published by a group out of Canada. And Dave Bergman, Dr. Lucas, Dr. Barnes, Russ Humphreys, myself, we're all listed in there. But you've got many competing models, some of which overlap with the common sense science model, but they're not necessarily based on our model. So the no part of the answer is that I'm not aware of any new scientists who are adopting it. And possibly part of that is with Dave Bergman's death and Bill Lucas's limited and increasingly more limited ability to speak and to write and publish. You've got a declining influence from this work in the world.
Can you hear me?
Yes,
Go
Ms.
ahead,
Christine,
yes.
go ahead.
Oh, I so appreciate what you're giving and how it makes sense of the things that always puzzled me. Like mass, that's just totally illogical the way it's taught. And the how can you have, you know, all these protons stuck together? Well, they said the neutrons must neutralize it, but it's like it doesn't make sense. It's never made sense. And I'm not a physics major at all. I'm just a gal who went to high school and thought about things. And this makes, I just love it. I just need to understand more, but I love it.
Well, thank
Okay.
you. It's kind of you to say.
Yeah.
Obviously, the whole scientific community is not coming on board with this. And, you know, it does such a wonderful job of explaining the data. But it reminds me of Thomas Kuhn's observation that progress in science does not come incrementally with new information, but it comes when the gatekeepers leave the scene and
Yes.
young people are willing to take the risk of embracing a new approach. What's it going to take?
I don't know. That's a great question.
I remember in the newspapers when they brought out plate tectonics, I thought this makes sense. And of course it was slammed. It was really slammed and now it's accepted. So it is possible, though maybe it may be more difficult in this field.
Well, many things in life are such that the more those who wish to claim that there's consensus, right? We only want consensus, science by consensus. The louder they are, the more you probably should look at the things that they don't like. just as a thought.
Yeah.
It's often the outliers and the new mavericks who push science forward. And you can find that in science history over and over again, by the way. So it's not me inventing something to be said here in defense of our theory. I think this theory has a great deal of merit, and to my knowledge, the common sense science theories of particles and the force law and so forth are consistent with more experimental data and measurements than any other single physics system in existence. But that doesn't matter to a lot of people. To a great many people, the existing mathematical models, the quantum model approach with the standard and general relativity theory approaches have been good enough. They're sufficient. Why are you fussing about it? Type of a thing is the attitude that many take, and I understand that attitude. disagree with them.
I'm a pediatrician and I look at child development. Young children reflect their parents' opinions. And then often adolescents go through a phase of rejecting their parents' opinions, but ultimately it goes to whatever the cool people say. And that doesn't go away in 7th grade. I see it in our senior community. How close are we to a computer model? And I see Gary Alcesser, you're there. And I know you were involved in a trial early on. Has the new information made that more workable?
Well, Gary's always been a good supporter. Thank you, Gary. And if I ever get any significant scientific funding to do research related to this, Gary's getting a phone call. Okay, I'm to do some of this computer modeling work, as are a few other friends of mine I've collected over the years, knowledgeable people. But the short answer is there has been no support. You're not going to get support from the normal funding sources for this type of alternative work. Doesn't matter how accurate it is. It really doesn't matter. The accuracy or the conformance with data doesn't matter. Okay, because popularity, what you'll get funding for, what the mainstream says is okay, what the publications and the gatekeepers, which would be peer review. By the way, Einstein was not peer reviewed. 100 years ago, people were not peer reviewed. If you had a scientific theory, you published it. Period. All right, it got free air. Other scientists looked at it because they wanted to look at all of them. But now there's so many papers and there's all this peer review process, which means for each discipline, for each little silo of information, even within physics, there are multiple separate silos with different belief systems. If you're a string theorist, if you're a quantum electrodynamics person, if you're gauge theory, etc., you know, there's a collection of different emphases that have their own journals and their own gatekeepers for the purity of their thinking. So it's difficult to break through that type of a system. We'll have to get independent funding, Lord willing, someday, and have some incredible commercial success using this model, and then people will pay attention to it. But until such time, just based on liking the ideas, having feeling like they make sense, that kind of thing means nada. Unfortunately, we'll have to do some kind of major breakthrough, I think, for there to be more wide examination of the model. Yes, sir.
What level of mathematics does a guy need to understand this theory? A little bit of vector calculus or what? Linear algebra?
If you're good with algebra, the mathematics will, if you're good with algebra, the mathematics will make sense to you. Now, I'm pretty good with calculus, but I would have to go back and study things again to be able to check Bill Lucas's homework in his publications. Okay. In other words, could I detect a math error? No. Okay. Could I go back and study like I did when I was at Georgia Tech and I knew calculus forward, backward, and sideways, and then be able to check his homework? Yes, I could. All right. But good mathematicians can check this work, but to understand it, to get a feel for what is the math saying, then you just need Wikipedia and a good understanding of algebra and how things add up, and you're good to go.
All right. Well, thanks a lot.
Thanks for being here and hanging in there so long. Brave crowd here to be here for an hour and back.
I think there's a lot of not thinking. There's a lot of narrative that everyone buys into this one and that, and very little thinking, because here I can see how this makes sense with what I was thinking in high school. And that's not hard for me. Now, maybe I just haven't been brainwashed. I don't know.
Well, we think physics should be physical and it should be understandable.
Yeah.
And the name of our organization, people ridicule it. Ridicule it.
Yeah.
All right, common sense science. How dare you? You know, hate it for you. You know.
Well, thank you very much, Glenn, and thank you, all you folks who found your way over here and you stayed and came up with some good questions. And I hope that you'll all look at the video so you really fix this in your mind. I think you probably have done the coursework for an advanced degree. Now, you won't get it until you write the thesis, but this lecture alone should qualify you to be considered
Glenn?
for a degree. Thank you very much.
Everybody gets a diploma. Gary, is that you asking a
Yeah.
question?
I was going to say, one of the big philosophical questions that come from any of these physics theorems is where does determinism versus, shall we say, a freedom factor involved? Because if you have a strict determinism model, then everything is fixed. There's no provision for the will or.
Yep. Carry on.
And that's an interesting.
You have a question
conundrum.
in there, right? Okay.
Well,
Yeah.
because you like to be able to boil things down into a state system where the next state is determined by the present state. But then
Well,
if you follow that
engineers
through,
like you and me like that. Yes. Carry on. But go ahead.
you're in big trouble at some
That's
point.
right. Well, the thing I come back to is God made this universe very discoverable for us and told us to go out and discover it and to conquer it and to control it, to own it. All right. So we know we can do that. But, the scripture does have that interesting saying that God holds all things together, that he is the one in whom all things consist and hold together. So even though we can describe this in scientific and mathematical terminology and use it, like an engineer or a scientist would to predict things and, control objects and invent stuff and so forth. The notion that God's spirit, and hence he made our spirits after his own, spirit is somewhere involved in this because we know that we influence our world. So we can't rule it out, but I can't show you the math for it either, Gary.
Well, and whenever you try to model these things with the computers, you've got measurement error on your input. You've got this nasty thing called floating point numbers, which are a very crude approximation to real numbers. And then you've got the fact that you're going to simplify your math at some level because you have trouble getting a closed form solution to a lot of equations to begin with.
Yep. We've been simplifying math for a long time. Simplifying it too much. But yes, great thoughts.
I threw a
Okay,
question
well,
at the beginning
let's
about
all,
you've got
let's
an
all
arc
meet again
term.
in 1 month. When Dr. Collins joins
Please.
us again.
I promise the next talk won't be as long. So I'll limit it to 1 hour. If you can tolerate it next month.
Thank you. This was wonderful. Thanks.
Can we stay online for those who want to talk?
Yeah, just the line can stay open. Those of you who
Okay. Gary, you had some other thoughts there? That,
Well, early on, you had an equation that had an R squared term and another square term times theta squared in it, the denominator. And I have no concept of how large R is relative to that other term.
to my understanding from the mathematics, R is a unit vector because it's just simply describing the orientation of the coordinate system. All right. So if you've got a XYZ three-dimensional coordinate system, R is the unit vector, that's one in each direction. So
Because you had a difference underneath a radical in that denominator.
yes,
And the second term was cubed.
correct.
And so if that second term gets it all small, it's going to disappear much more quickly than the first term.
Yes, it will. But then because it's cubed, as the velocity gets bigger, closer to C, then that term gets bigger faster.
No, it's not the same color.
Because it's 1 minus 1 unit. It's the denominator will approach 0, making the whole value bigger.
So it's maybe on my computer.
Yeah.
But if you like the mathematics aspect of this, Dr. Lucas' book, The Universal Force, Volume 1, is for you. I reread the whole thing in preparation for this talk, so it can be done.
I'm much more conversant in discrete math than I am in this differential operator notation stuff.
You're a Z transform kind of guy, aren't you? That's right. Okay.
Combinatorics, number theory kind of thing.
All right.
Have you seen Nichols' book, Mathematics is God Silent?
No, I haven't. Nichols. Okay, let me write that down here.
He deals more with applied mathematics, although there is a chapter with quotes from various physicists about mathematics working better than they have any reason to expect. It's like that.
Yeah. Okay. That sounds interesting. I'll check it out. Thank you. Other questions,
Yeah.
anyone? Brian, thank you for attending. I have 2 friends named Brian. I have a Brian Cook in Nashville, Tennessee, and Brian Schrader out in Texas. So I don't know which Brian this is. It's always just been Brian. So you can send me an email and let me know. Thanks for listening. Gary,
You know,
other
in the
thoughts?
computer field, the small scale stuff is becoming very, very important.
Yes, it is, isn't it?
You get down to 3 nanometer resolution, you're pushing things.
Yes, we are. TMC can do that, can't they? That's the semiconductor manufacturer in Taiwan, TMC. Can't they
Yeah,
do
we got to
3
get smarter
nanometer?
about that. Not
Yeah,
be
okay.
so dependent on that.
How about that? Yes. Yeah, they're doing mostly 5 nanometer right now. I think that's kind of their mainstream stuff, but none of the other facilities in the world can do 5 nanometer. They're all at 7, I think. It's my recollection of current state of the art anyway.
And now the number of cores you're getting on a chip is getting to be pretty significant.
Oh, yes.
It used to be a big deal to have 28 processors in one machine. Now you've got far more cores than that on one chip.
Exactly.
And it used to be a big deal when you got to 32 processors. Now we've got machines with 300,000 cores.
Yeah. I
And
love
some
it.
of them a lot larger.
I've got in the backup slides, there's one little slide, if you get a copy of them, Gary, on quantum computing. And a company, I can't remember the company's name right now, but they are relying on a particle called an anyon, A-N-Y-O-N, which is one of the 33 quasi-particles that allegedly exist in their model system. But they're using what are non-complementary anyons, which means that if they swap position, they don't just return to their normal state. So you can store information in them. So they're using it like a gate, a physical phenomenon that functions like a NAND gate kind of thing to build a quantum computer with. And they're still trying to get the superposition and the entanglement characteristics that they see there, you know, to make the exponential gains that you get with a quantum gate model. So, interesting stuff.
I think 54 qubits is the largest I've heard of being built.
128 IBM. And they're the ones working on the best error correction or error detection, which is the key to error correction model that's going to make their machine, they claim, much more useful than the other quantum computers have been thus far. So, but anyway, that's a rapidly changing field. So, you know, wait a minute and you miss something. So it's hard to stay up with it. Let's see. I've got 2 things in chat. I better look at that. All right. Oh, that's you there asking about determinism. Okay, got it. All righty. Hello there.
I don't know if you can hear me without the mic. Can you hear me at all?
Yes, sir. I hear you from the computer right there.
Now, your model is quite a bit of changes from the standard model. What about on the Planck scale? Does that still go with the regular agreed upon stuff?
No, sir. There's the whole section in the appendix of this briefing that we didn't have time for, called the subatomic model, actually the subparticle model. In other words, we spend some time looking at an individual particle made up of multiple fibers, and if you busted that apart, this is the source of pions, mesons, muons, kaons, etc. You know, the particle zoo, as it's called in particle accelerator world physics. And so we have a model that in a sense shows where all these particles, or they're not really particles because they're not stable, they're pieces of particles. We can explain where these pieces come from in a physical model type of explanation. Planck's constant is an interesting one in that it's used for what's called the Heisenberg uncertainty principle, much heralded. But for example, if you just take the hydrogen molecule, which is made of those four particles, 2 protons, 2 electrons, we know how big a hydrogen molecule can get, kind of the limits. So we know that within a certain size, there's, let's say, 2 electrons banging around in there. So we know the position of those electrons with at least that much certainty, right? They're inside this much space. But we also can calculate the energy of these particles. And if you multiply the position and the energy together, you're supposed to be limited by Planck's constant. But as it turns out, you're not. In other words, the Heisenberg uncertainty principle only applies to certain circumstances. And that may be the majority of circumstances, but it's not all circumstances. And modern physics has not acknowledged that, even though there are plenty of experiments that show that the Heisenberg uncertainty principle is violated. So our model is still physical. We know the origin of Planck's constant is conservation of charge and magnetic energy. All right, conservation of energy, that's where it comes from. So if there are circumstances where it's broken, then we're just not understanding the circumstance physically correctly. And that's what, of course, is going on. But you would probably, you might enjoy reading about the particle model that Bill Lucas has developed.
All right, thank you.
Thanks for asking. I hope that was helpful.